Hey everyone, welcome to Brain Attic. So today we are going to talk about trip point voltage in case of CMOS inverters in CMOS inverters. So if you're aware, the current technology in the VLSI industry heavily depends upon the CMOS. And a good starting point to understand what is CMOS is to understand the CMOS inverter. So we'll look into the schematic just for understanding. The schematic of an inverter looks like this, and in the CMOS logic, it will look something like this. Where on the top you will have the PMOS, and on the bottom you will have the NMOS. This is our VDD, and this is ground. We have Vin, which is the input voltage at the gate of the PMOS and the NMOS, and we have Vout, which is getting from this terminal of the PMOS and the NMOS. Now, another very important thing while discussing about the CMOS inverter is its voltage transfer characteristics. Voltage transfer characteristics. Something very simple and often asked while discussing the CMOS inverter. So we'll draw the voltage transfer characteristics of the CMOS. We'll have V out on the y-axis and V in on the x-axis. We'll just highlight the VDD for our reference, and this is our zero voltage. So the voltage transfer characteristics will look something like this. Now, we'll draw another line which is y is equal to mx, which will intersect. Sorry, we'll just redraw this. We'll draw a line y is equal to mx, which will intersect the voltage transfer characteristics. This point is what we call as the trip point. We'll see it as Vm. So Vm is nothing but our trip point voltage. Now the next thing which we are going to do is basically divide the voltage transfer characteristics into 5 regions. Why we are dividing into 5 regions, we'll know it in very short time. So in this region, if you see, my PMOS is in linear region and NMOS is off. In this region, you will see that the PMOS is still in linear while the NMOS has entered saturation. In this region of the voltage transfer characteristics, you will see that the PMOS is in saturation and the NMOS is also in saturation. In this region, the PMOS is in saturation, however, the NMOS has entered the linear region. And finally, in this region, the PMOS is off and the NMOS is in linear region. Very evident, right? When PMOS is in linear region, you have the voltage transfer characteristics at VDD, and when the NMOS is in linear region, you have the voltage transfer characteristics at 0, almost 0. Now, moving ahead, what we are going to do is that we are going to derive this short channel, this trip point voltage for short channels. Now, if we know that in case of short channel MOS, we encounter velocity saturation even before the regular saturation. Just for understanding, I'll draw the IDS versus VDS graph for the MOS for an NMOS. So what we experience is this. This is, let us suppose, our VGS minus VT. But in case of short channel devices, we often see that the saturation comes even much before. Let us call this voltage as VD sat, and the current saturates here itself. The reason for the saturation is velocity saturation. This came into observation especially for the short channel cases. Now, let us make some other assumptions. So what is our first assumption? Our first assumption is that both NMOS and PMOS are in velocity saturation. We also assume that lambda n and lambda p are equal to 0. This will be better if lambda n is equal to lambda p is equal to 0. Now, our VGS_n will be equal to Vm. Our VDS_n will also be equal to Vm. That is the VGS for NMOS and VDS for NMOS. Our VGS voltage for PMOS will be Vm minus VDD, and VDS for PMOS will be Vm minus VDD. Now we know that the current in both the cases will be equal but in opposite directions. So we can say that IDSN is equal to minus of IDSP. Now applying the equation for the velocity saturation, current equation for the velocity saturation region, we have Kn prime Wn by L into Vd sat n Vm minus Vdn minus Vd sat n by 2 is equal to minus Kp prime Wp by L Vd sat p Vm minus Vdt minus Vdp minus Vd sat p divided by 2. So here you see, right, I am applying Vm and Vm minus Vdt. Let us introduce another variable. Let us say R, which is nothing but equal to Kp prime Wp Vd sat p divided by Kn prime Wn Vd sat n. This simplifies our equation a lot. We'll see. Vm minus Vtn minus Vd sat n whole divided by 2 is equal to minus R Vm minus Vdd minus Vdp minus Vd sat p divided by 2. Eventually, Vm 1 plus R, taking the Vm terms on the right side and sending all the other terms to the left hand side, we are left with R into Vdd plus Vdp plus Vd sat p divided by 2 plus Vtn plus Vd sat n divided by 2. This brings us to Vm is equal to R into Vdd plus Vdp plus Vd sat p by 2 plus Vtn plus Vd sat n by 2 whole divided by 1 plus R. Therefore, you got your trip point voltage equation. Now, if we want to make this even simpler, right, we can make some more assumptions. We'll make some more assumptions for a better, more compact result. Let us assume that your Vd sat n is equal to Vd sat p, and your VTN is equal to minus VTP. Let us also assume that your width of the PMOS device by width of the NMOS device is inversely proportional to the mobility and the capacitance factor K prime, Kn prime, and let us be equal to 2. This leaves us with R is equal to 1. Now we'll see that if we apply all these assumptions, then we are left with a very beautiful expression for Vm, which is nothing but Vm is equal to VDD by 2. So this over here is your trip point voltage for short channel devices. And if you apply, that is the trip point voltage when both the PMOS and the NMOS are in the velocity saturation. By applying some more assumptions, you can bring the expression to Vm VDD by 2. If you do like this video, please hit like and subscribe to my channel for more content like this. Thank you so much.